And welcome back as we continue our cosmic journey through our own solar system. We've, of course, been talking about a couple moons in our giants. So let's go ahead and shift our focus away from the Jovian moons to that of Titan and Triton. So let's start first with Titan, which is a moon that actually has an atmosphere. Titan was the first moon discovered after Galileo saw the four large moons of Jupiter. Now, Titan has roughly the same diameter, mass, and density as either Callisto or Ganymede, and presumably also has a very similar composition, that being about half of ice and half of rock. However, Titan is unique among the moons with a thick atmosphere and lakes and rivers and falling rain of hydrocarbons just as ethane and methane. Now, Titan is the only moon or planet other than Earth where we have found evidence of bodies of surface liquids. All the rest of them, we assume there might be, but they're probably underneath. Here, we actually have seen some evidence of it. Now, why does Titan have surface liquid? Well, to answer that, we first need to look at Titan's atmosphere. The 1980 Voyager flyby of Titan determined that the surface density of its atmosphere is 4 times greater than that of what we find here on Earth. Now, the atmospheric composition is primarily nitrogen, an important way in which Titan's atmosphere actually resembles Earth's own. Now, while Titan is colder than our planet, the red line that we can see here in this image really kind of indicates the temperature of Titan's atmosphere at different altitudes. So if you notice, as we start moving up in kilometers here, we have a surface temperature here around a little under 100 Kelvin. It, of course, decreases, but as we move up through this methane and ethane layer, you can see there's actually a particulate rain layer here. And we also have kind of a thick photochemical haze that helps trap in some of this heat here. So even though the surface, might be, again, not what we expect to be, we have all these different things here with this nitrogen atmosphere kind of keeping some of this heat trapped in here thanks to this atmospheric composition that actually is retaining some of these things. And again, remember, this is a 4 times greater atmosphere than that of Earth. Remember, we looked at something like Venus. Venus also has a thicker atmosphere, and because it has a thicker atmosphere, it's actually able to retain heat very well. So, as we start breaking down the atmospheric composition, Voyager detected, as we mentioned, hydrocarbon compounds that indicated that there must be an active chemistry in which sunlight interacts with atmospheric nitrogen and methane to create a rich mix of organic molecules. Now, there are, of course, multiple layers of hydrocarbon haze and clouds in the atmosphere, as we saw just a moment ago in that diagram. Now, these Voyager discoveries motivated a much more ambitious exploration program using the NASA Cassini Saturn orbiter and a probe to actually land on Titan called Huygens. So, what did we find when we started probing Titan's surface? Well, Huygens probe successfully photographed the surface from below the clouds. Now, the photos taken during the descent showed that we had actually a variety of features on Titan, including drainage channels, which suggested that Huygens had landed on the shore of an ancient hydrocarbon lake. Now, the sky itself was a deep orange, and the brightness of the sun was 1,000 times less than what we expected to find on the sunlight on Earth. Now, Titan's surface temperature was about 94 Kelvin, or negative 179 degrees centigrade. Now, granted, when the warmer spacecraft heated enough the ice where it landed for its instruments to measure, it released hydrocarbon gas. Measurements on the surface continued pretty much for more than an hour before the probe actually succumbed to the frigid temperatures that were present on Titan. So when it took pictures So when we got pictures of the surface of Titan, we got some interesting views, as we already mentioned. The left image shows the views of Titan from the descent camera in flat projection at different altitudes. So as the probe was descending to the surface, it took, of course, these images. So 150 kilometers, we have that kind of the haze that we were talking about. At 15 kilometers, you can see we were starting to get a little bit more view of some of this mountainous surface. And 2 kilometers and then 0.4 kilometers, where we're getting, again, those drainage lines that we were talking about. The right image here, which was taken after the probe landed, shows a boulder-strewn surface illuminated by a faint reddish light. Now, these boulders aren't the typical stony boulders that we expect here on Earth, but instead are composed primarily of water ice. Now, what about the Cassini probe? What was its imaging of Titan like? Well, radar infrared imaging of Titan from the Cassini orbiter built a picture of a remarkably active surface on this moon. There are large methane lakes near the polar regions that interact with the methane in the atmosphere. Now, the presence of many erosional features indicates that the atmospheric methane can condense and then fall as a form of rain and then flows down valleys to the big lakes that our probes were sitting in. Now, Titan has a low atmosphere equivalent of the water cycle on Earth, but instead of being the water cycle that we're familiar with, it's a combination of methane, ethane, and a trace of other hydrocarbons. And so when we actually looked at the lakes that we found on Titan, we can look at this false color image here that shows some of those liquid lakes on Titan. And this mosaic of Titan's surface shows in detail a high ridge area and many narrow, kind of sinuous erosion channels that appear to be part of a widespread network carved by flowing hydrocarbons. This is exactly the kind of surface detail that we expect, for example, here on Earth, if this was a river and it was splitting off into smaller little branches here. Now, these discoveries have begged the question of if there could be life on Titan. So, shifting away from Titan, let's go ahead and look at Triton, which is Neptune's largest moon. Neptune's largest moon, Triton, has a diameter of 2,720 kilometers and a density of about 2.1 grams per centimeter cubed, indicating that it is probably composed of about 75% rock mixed with about 25% water ice. Now, the measurements indicate that Triton's surface has the coldest temperature of any moon we've explored, as its reflectivity is very, very high, about 80%, which means 80% of the sunlight that does actually reach it is reflecting back off the surface. Now, Triton reflects most of the solar energy that falls upon it, resulting in a surface temperature that's between a very frigid 35 and 40 Kelvin. So that is a pretty low temperature. So what we see when we look at Triton's surface and atmosphere is that the surface material is actually made of a combination of frozen water, nitrogen, methane, and carbon monoxide. Now, methane and nitrogen exist as a gas in most of the solar system, but interestingly enough, they are actually frozen at Triton's temperatures. Only a small amount of nitrogen vapor exists to form an atmosphere here on Triton. Now, although the surface pressure of this atmosphere is only about 16 millionths of a bar, so it's very, very tiny, this is sufficient enough to support thin haze or cloud layers. So what do we see if we look at the surface of Triton? Well, we start seeing a long geological evolution. Although some impact craters are found on Triton, many regions have been flooded fairly recently by the local version of lava, which many think it's either water or water-ammonia mixtures. There are also mysterious regions of jumbled or mountainous terrain. Now, there is a polar cap on Triton, and it covers much of the southern hemisphere, apparently evaporating along the northern edge. Now, this polar cap may consist of frozen nitrogen that was deposited during the previous winter. Now, you might be wondering, if Triton's so cold, how does it start getting all these different surface features? Well, Triton does have geysers that are active on its surface. The evaporation of Triton's polar cap generates actually geysers, or volcanic plumes of nitrogen gas that rise about 10 kilometers high, visible within the very thin atmosphere. Now, these plumes differ from the volcanic plumes of Io in their composition, and also that they derive their energy from sunlight warming the surface rather than from an internal heat source.